Good morning. A couple housekeeping things before we continue. Friday, today, 3 to 4 p.m. are my office hours. Can I get a rough show of hands to see who, I won't hold you to this, but who might be interested in going to office hours? It just depends on where we meet. Okay, so I'll plan on being in the atrium. We'll just move some of the chairs together and we'll meet there instead of my office, just because we had several hands go up. Also, Monday's TA office hour, because it's a holiday, will be on Tuesday instead. And that's at 1 p.m. in the SME atrium. Any questions about the class or what I said before we go on?
So this TA office hours normally from 12 to 1 p.m. Is that correct? It's just 1 p.m.
You want to do it at what time?
1 p.m. Tuesday works better.
1 p.m. Tuesday.
And if
just
you guys,
this next week only.
But
Generally the syllabus will be correct, but next week 1 p.m. SME atrium. Okay, anything else? Cool. So last time we ended class with a discussion of what happens when light interacts with a molecule or a nanoparticle or a surface or a semiconductor. A lot of different things can happen. And it's the basis of why things look the way they do. It's the basis of technologies like anything based on spectroscopy, anything based on colorimetric changes in a nanoparticle in response to, say, drug levels or, say, a pregnancy strip or anything that involves light-matter interactions. And in general, three things happen: scattering, absorption, or nothing. And with the exception of nothing, scattering and absorption can be further subdivided into a couple of different categories. So we talked about scattering, elastic scattering, Rayleigh scattering, where a photon transiently polarizes an electron cloud in some particle, molecule, or object, and then upon depolarization of that electron cloud, photon is re-emitted at the same wavelength as the incoming photon. So that's elastic scattering. Inelastic scattering is where you have some molecule or material or nanoparticle or surface that has some vibrational state associated with some part of it. So molecule is vibrating and then a photon comes in and the vibrational state of the molecule changes. Often it can either lose energy or increase in energy. The one that we normally see, what's called a Stokes shifted process. Don't worry about memorizing that. What happens is the molecule increases in vibrational frequency and the photon therefore loses energy. And in that case, if we know the energy of the photon that went in and we can measure the energy of the photon that came out, we know what the difference in energy of the molecule was before and after this inelastic scattering process, which is pretty useful. And at the end of class, I mentioned something called surface-enhanced Raman scattering. Or SIRS, which is really a quintessential nano engineering phenomenon, or phenomenon that's useful in nano engineering. And I wasn't going to go into details on this. I just wanted to say what it was, but because there were some questions about it after class, I thought I would just elaborate for a minute. If you have a surface of some metal, we picture metal surfaces as being shiny and smooth, but if you look at them very closely under an atomic force microscope or even an electron microscope, you'll notice that there are asperities and dips and surface roughness that can be on the order of several nanometers even, and it still looks like a mirrored surface. And what happens is that some of these surface asperities, these nanoscale surface asperities, have these conduction electrons that will resonate with a particular wavelength of light that's irradiating the nanostructure. And what happens is that the electric field, as that light is scattered, the electric field is intense around the surface asperities. And this works not only for rough surfaces, but also intentionally designed nanoparticles, say nanocrystal that looks like a triangle. We call these spots antennas, antenna. I don't know how to spell it. Antennas, antenna. And what happens is that when there's a molecule in the vicinity of one of these metallic nanostructured surfaces or particles, the Raman scattering, the probability that a molecule will undergo Raman scattering goes way up by many, many orders of magnitude. So this can be used as a spectroscopic technique. For example, if you put nanoparticles in the bloodstream and you shine a Raman laser at them, the scattered, and there is some molecule of interest in the bloodstream, and you have some optical window with which you can look at it, and you measure the scattered photon, you can measure the presence or absence of these molecules, say, in the bloodstream or in a cell, in some biological milieu. Yeah.
What sort of computational power is necessary to make sense of those results? Is it something a phone could do, or do you need big equipment?
That's a good question. So the question was, what sort of computational power would you need to make sense of those measurements? It probably depends on the time resolution that you need. In general, the wavelength resolution doesn't really produce that much data, but if you have many signals, it probably requires some serious deconvolution. That's a good question. I haven't really thought about it. Okay, so absorption. Absorption electromagnetic energy can be accomplished through a few different molecular mechanisms. In the low energy regime, we have rotational and vibrational vibrational modes that appear in the IR. And these are quantized differences in literally the frequencies at which, or the oscillations of electron density in a molecule can go. So, for example, you have some modes that are higher in energy than others. So the nuclei and molecules will shake back and forth, but if you have a more complicated molecule, you might have bending and breathing modes too, and it takes certain amounts of energy to get from, it takes quantized amounts of energy, so that is set differences in energy to get from one vibrational mode to another. And we can use that in in vibrational spectroscopy. In fact, the Raman scattering in general is related to vibrational spectroscopy, and you can actually access some of these modes using the Raman effect. So as I alluded to, you can watch you can measure the differences in vibrational frequencies by probing with a laser and then measuring the difference in energy of the scattered photon. electronic absorption is more familiar to us as a day-to-day phenomenon because things have colors, and that's largely a result of electronic absorption. And electronic absorption can really be UV, visible, or IR, generally near IR, so higher energy IR wavelengths.
Hello. In the lecture today, I made a little bit of a mistake when I was talking about the absorption and emission from the valence band to the conduction band. I actually had the nomenclature backwards, and I think I said it wrong a few times later on in the lecture. I'm sorry about that. I hope to make amends right now and make sure that I explain it correctly. So, in the case of electronic absorption, what happens is that a photon comes into a material, and this could be a quantum dot or a semiconductor or a bulk semiconductor or really any material, but we think about it particularly in the cases of materials that absorb in the UV, visible, and near IR regions of the electromagnetic spectrum. So in a case of electronic absorption is the promotion of an electron from the valence band to the conduction band. And a diagram is as follows. So suppose you have two band edges, and later on today we will talk about the band edges in the form of molecular orbitals of beta carotene. And we have an electron here, and this is the valence band, and this is the conduction band. And what happens when a photon comes in, and a photon is given the symbol h nu, or this is Planck's constant, and nu is the frequency of the photon. What happens is that a photon is absorbed here. And the next state that we have leaves a hole, sometimes called little h with a plus. This is not Planck's constant, and it's definitely not a hydrogen ion. It's a hole. Sometimes it's called an electron hole because an electron is missing from the valence band, and the electron is now somewhere here in the conduction band. And it doesn't go necessarily, unless you're really lucky, exactly up to the band edge. What it does is it can overshoot, and it overshoots with a probability based on what's called the density of states above this band edge, because you could have say a low density of states here, and then maybe a high density of states here, and then maybe lower over here, and maybe higher up here. And it depends on the idiosyncrasies of the material that you're using. And this is why when you take a UV visible spectrum of a quantum dot or a semiconductor or an organic dye, you don't get just a line that corresponds to exactly the band gap. You usually get a broad, lazy absorption, and that is due to the fact that we have densities of states both in the valence band and the conduction band. So what happens after absorption, typically, is that this electron is high in energy, and usually over a very short time scale, it will kind of find its way to the band edge. And we call this process thermalization. Thermalization to the band edge. And what happens when the electron thermalizes, and now it's back to the band edge, is that this energy is given off as heat, or molecular vibrations. Molecular or bond vibrations. So now we are at the band edge, and this loss in energy here is important to understanding why a fluorescent photon, and we'll get to that in a second, has less energy than the photon of excitation under normal circumstances. So then what happens is emission down to the valence band. And it doesn't necessarily have to go exactly to the band, to the valence band edge. It could overshoot. It depends on the density of states in the valence band. But in general, this the photon that's emitted here, we'll call this H nu prime. This is a photoluminescent photon. And this could be one of two types of photoluminescent photons. It could be a fluorescence event. Fluorescence is the normal case where an electron goes up to the valence band, up to the conduction band. Sorry, there I go again. I don't know why I'm doing that. Goes up to the conduction band, thermalizes to the band edge, and then goes back down to the valence band, concomitant with the emission of a photon with the energy that is equivalent to the gap, the amount of energy that was traversed here. We can also have phosphorescence. And I won't go into details onto phosphorescence. You can read about it on your own if you'd like. But basically what happens in phosphorescence is that somewhere up here, the electron changes its spin. So spin, it could be spin up and spin down. When electrons are in the same molecular orbital or the same band, and occupy the same energy, they can't have the same spins, so they have opposite spins. But then when one electron is promoted to the conduction band, some event can happen, and some materials are better at doing this than others, that the spin can switch, and now it can't go down again. So it has to. So there's some long process that it takes in order for the spins to be anti-parallel again, so that the electron can go back to the valence band. And that is a long process in phosphorescence. And for some materials, phosphorescence can take place over the time scale of minutes. It can take minutes for the electrons in a phosphorescent compound to return to the valence band, and that's the basis of glow-in-the-dark materials. So some of you may have had, I did, have those stars, those glow-in-the-dark stars on your bedroom ceiling, and then over the course of the night they slowly die down to nothing. So this is electronic absorption. And what else can happen after absorption is you can either have de-excitation somehow or transfer. So de-excitation, this is de-excitation of an absorbed photon. De-excitation of an electron that it was promoted to a higher energy level because of an absorbed photon. And de-excitation has a couple of routes that it can take. Non-radiative. In this case, it's like thermalization, but the energy of the electron goes to bond vibrations and heat. Or you can have what are called radiative de-excitation, which is photoluminescence. And again, this is fluorescence or phosphorescence. Or you can have transfer of the excited state energy. Transfer of the excited state energy can happen in a number of ways. For example, if you're up in the conduction band and there's another species nearby that has a lower energy conduction band, the electron can go from one conduction band to another conduction band, and then so on down. These types of transfer processes are the basis of how photosynthesis works and solar cells work, and so that's something that can happen. You can transfer the energy. You can also have emission of a photon, and then absorption of the photon by another species, or you can have the wave functions of an excited chromophore and a ground state chromophore. By chromophore, I just mean a system of valence band and conduction band systems that absorb light. So chromophore, chromo, color. So what you can have is the wave functions of an excited state chromophore and a ground state chromophore overlap, and then you can actually transfer the energy from one to another without involving the emission of any photons whatsoever. And the third alternative is that nothing happens. So nothing happens when a photon comes into contact with some matter. There's a probability associated with what's called the absorption cross-section of the material, which are not the same for every structure. That depends on the details of the molecular quantum mechanics, and don't worry about that for our purposes. All right, thank you. Back to the classroom.
Okay, let's use what we have learned about emission, absorption and emission to answer the question, why are carrots orange? Of all questions. One of the effects of size confinement is of quantization of energy. And in fact, when you have a semiconductor or an organic dye and you shrink it down, you just make it smaller, you remove atoms and stuff, you actually change the allowed energies of a particle confined within that space. And this is one of the key properties of nanostructured materials, particularly nanostructured semiconductor materials, which are important in imaging, computation, bioimaging, biosensing, solar cells, let's say, I'm making this up, 75% of nanoengineering is due to size confinement of electronic structures. Of course, when I get to the bio applications, I'm going to say 75% is due to the ability to interact with biomolecules on the right scale. But anyway, it's a big deal. It's a big deal. Anyone ever heard of the particle in a box, maybe from a chemistry class? Okay, so that's sort of a model, and we're going to explore it here in the context of an organic semiconductor that says that when you shrink the size of the box, you increase the energies of the allowed wave functions of that particle, in this case an electron, within the box. The more confined it is, the higher in energy it is. You can think of it like if you're stuck in your house all weekend because of a snowstorm, which they don't have in San Diego, but suppose they did. If you're stuck in your house and you're confined, you start to freak out because so you're bouncing off the walls, you have really high energy, and that's what happens. That's what happens to particles. Whereas if you're, well, I don't know, whatever. Okay, confining particles. The particle in a box and what we hope to do is answer the question, why are carrots orange? Okay. I'm going to draw an organic structure on the board, and organic chemistry is not required for this class, but I'm going to teach you what you need to know in the next 5 minutes. Do not freak out as I draw this. First, you draw your TV with the rabbit ear antennas. This is called beta carotene, called carotene because it was derived from celery. Just kidding. Biosynthetically, what this is derived from is another molecule called isoprene, which looks like this. What on earth do these lines and angles mean? I'll tell you. First, I want to say beta carotene. You can actually make a solar cell out of beta carotene. You can take a carrot and squeeze it and like wring it out like a towel and get the orange juice that comes out, evaporate all the juice, take out all the salts and stuff. You're left with some other stuff too, but a lot of beta carotene. And if you actually put that beta carotene, and assuming it's purified enough in between two different metals and shine light at it, assuming one of the metals is thin enough to allow light through, you can actually make what's called a Schottky photodiode, which is a solar cell. It's going to be a pretty crappy solar cell, but it will work. It will actually, if you had like a room of carat solar cells, you could probably power like 1/100th of a pixel on a digital watch, but it would work. And you can make materials deliberately that work a lot better than beta carotene, and therefore, you can power like a few light bulbs. Oh, solar energy! How I love thee, but how depressing you are. This is called a molecular semiconductor. So I want to give you an aside on how to read structures like that. So chemistry to me means transformation of stuff to other stuff and where electrons go from one molecule to another. But just to be able to read an organic structure, you don't need to know anything about chemistry. It's just like reading a blueprint. So this is an aside on organic structures. This is benzene. What does this really mean? Let me draw another one. Do we believe that's a molecule? It is. This is propane. And what did we do? Each kink here is a carbon atom. All the kinks in the structure are carbon atoms. So all these vertices are carbon atoms. Each carbon atom has 4 things bonded to it. If we didn't draw all the things that are bonded to carbon, then you assume that the missing elements to which carbon is bonded are hydrogen atoms. And those rules describe how we get from here to here. So the kinks and termini are carbon. Carbon has 4 bonds. The third rule is that hydrogen atoms are not, the H's are not drawn. Four is that all other atoms are drawn. It's ironic that organic chemistry can be considered, organic structures can be considered the structures comprising carbon and hydrogen, but it's ironic that carbon and hydrogen are the only elements that we don't draw. Okay. Beta carotene has a particular molecular structure which has these alternating double bond, single bond, double bond, single bond, double bond, single bond, all the way across the molecule. And what happens from general chemistry, we know that these sp2 hybridized carbon atoms have these figure 8 like orbitals that go in and out of the plane of the board. I see a lot of sighs as though you thought you'd never see this again and that it was very unimportant. What happens when you have lots and lots and lots of these orbitals, one after the other, is that an electron can live in this system and just go from one side of the molecule to the other with relative freedom. And what happens when you have that scenario is that the electrons can delocalize. This thing becomes a one-dimensional particle in a box, becomes the box for an electron that's one-dimensional, because the electron can live in these p orbitals, or these pi bonds between p orbitals that extend across the entire molecule. And as a result, the electrons have quantized energy levels, which produces a valence band and a conduction band, and therefore absorption by visible ultraviolet or near IR light. So we have 22 sp2 hybridized carbon atoms, and in each one of these carbon atoms, it contributes one electron each into this system of what's called pi conjugation, which just means alternating double single, double single, double single bonds. So we have 22 pi electrons. And from chemistry, we know that if we have 22 pi electrons, 22 sp2 hybridized carbon atoms, we have 22 molecular orbitals. Everything is 22 so far. Everything's 22 so far. But these orbitals, each one that forms can fit 2 electrons each. And because you don't want to have electrons that are way high in energy when they could have lower energy, you fill them up from the bottom. 2 in the first one, 2 in the second one, 2 in the third one, 2 in the fourth one, and so on. So the first 11 are filled, and the next 11 are vacant. So we call these 11 bonding molecular orbitals. And 11 anti-bonding MOS, molecular orbitals. Okay, now we go from one topic that you hated from chemistry to a topic that maybe you also hated from physics. And together, we'll combine them to answer the question, why are carrots orange? This is a one-dimensional box. It has sides that are infinitely tall, and the potential energy on the outside of the box is infinite. This is x-axis, and this will be 0, and this will be L, which is the length of the box. The potential energy inside the box is 0, so it's all kinetic energy inside the box. Schrodinger equation. What goes in the box? There's no other way to say it. Schrodinger equation. Okay. Not everybody's favorite topic, but here it is. It's the basis of why everything works. Something about a cat, I think. Schrodinger equation inside the box is minus h bar over 2m, where h minus h bar, or or h bar is Planck's constant divided by 2 pi. Times the second derivative of psi with respect to x, which is called the wave function. Psi of x equals the energy times psi of x. It's the only differential equation that we'll see probably in the course, and I'm going to solve it for you. What are the solutions? Well, what function is related to its own second derivative, but exponentials can be also sines and cosines. We have psi sub n of x equals the square root of 2l over sine n pi x over L. And the energies associated with these wave functions, the E sub n's, where n is an integer greater than or equal to 1, E sub n equals h squared, h is without the bar this time, n squared over 8 m L squared. What do these wave functions look like inside the box? For n equals 1, we call this the ground state. N equals 2, we call the first excited state. This is like an elevator in a hotel. N equals 2 is the first excited state. Just like when you go into the elevator in a hotel, they don't call the lobby they call the lobby the ground floor, not the first floor. Same convention in quantum mechanics as hotels. Unlike hotels, there will be a 13th floor. So this is psi 1 in the ground state. Looks like this. Psi 2 has 2 bumps, just one period of a sine wave with one node in it. And psi 3 is somewhere up here. Because of the square dependence on the n, the spacing between the levels increases as we increase the n. So we now have an electron. We're considering, well, we have 22 electrons in 11 bonding orbitals, which is psi 1 through psi 11 in this picture. And what we want to do is consider the lowest energy electronic transition that we can get, which is equivalent to bumping an electron up using a photon from psi 11 to psi 12. N equals 11 to n equals 12. And the difference in energy by that equation will give us the wavelength of the photon that it took to accomplish that jump. The wavelength that it took to accomplish that jump will be related to the color that the caret appears. So we have the change in energy from N initial to N final equals delta E from N equals 11 to N equals 12, where this is called the highest occupied molecular orbital. This is the lowest unoccupied molecular orbital. And what we want to do is measure the difference in energy between those. So we have delta E equals N final squared minus N initial squared. So just the difference in energy times Planck's constant squared over 8mL squared. M is the mass of an electron. And in this case, we have 23 h squared over 8mL squared. Now, what don't we know? We don't know L, but we have a picture of the molecule, so we can kind of take a guess at L just based on bond lengths. So if L is about 18.5 angstroms, that means I have 5 minutes left. L equals 18.5 angstroms. Some of you may wish to go home and figure out what L actually is based on the number of bonds, and it's going to be a bit higher than this. However, given the simplicity of the model that we know what it is based on second quarter or third quarter chemistry, we know what the model is, and the fact that we have a real molecule, the fudge factor here is not actually that high. So bear with me. Let's just say it's 18.5 angstroms long. It's a little bit longer than that, let's just say, because we made a lot of assumptions. So if L equals 18.5 angstroms, calculate the wavelength of the photon absorbed. So delta E equals h nu, which also, so nu equals c over lambda, which is nu equals hc over lambda, where this is the speed of light. Lambda is the wavelength. And I'll give all of these values now. And this is, again, 23 h squared over 8mL squared. And solving for lambda instead, we have lambda equals 8mCl squared over 23h. Now, if we add all the numbers in, we will get an answer, and we'll see how well we did based on this really simple model. So we have 8 times 9.1 times 10 to the minus 31 kilograms times 3, which is the mass of an electron, times 3 times 10 to the 8 meters per second, times 1.85 times 10 to the minus 9 meters squared. I've just converted to nanometers just so that we make the scientific notation more consistent, over 23 times Planck's constant, which is 6.6 times 10 to the minus 34 kilogram meters squared per second. And what we end up with is a wavelength of 490 nanometers. And just to show you the literature value for the maximum absorption wavelength is 470 nanometers. And again, I beg for forgiveness for making up the length of the box, but it's not that far off. or 2.5 electron volts. Electron volts and nanometers are related by the factor 1240 eV nanometers. So divide one by the other, one or the other, to get the other, if that makes sense. Okay, so why do carrots appear orange? If we draw our Roy G. Biv color chart, I swear I'm almost done. Where is 470 nanometers? Say somewhere around here, somewhere in the blue, in the low energy blue range, close to green. So if we absorb here, so we absorb, and because of the density of states, because we have a broad absorption, we're actually eliminating a big chunk where this is the max. And what are we left with? But mainly red and orange colors that are scattered. Scattered diffusely, which is why a carrot, because it's not a regular mirrored surface and doesn't look like a mirror, it's scattered and reflected, mostly scattered light. And what photons are scattered? The ones that aren't absorbed, so these ones. And that's why carrots appear orange. I will see you all on Wednesday. Thank you very much for your attention, and have a look at the homework.